Welcome to the glass plate. In this example we're going to consider the amount of work that a pump needs to do to pump up water from a lower to a higher position. We're going to compute how much of the energy of the pump is required for height and what are our frictional losses. Our system is the following. We have water flowing into a tube, and in that tube a pump is bringing the water towards a higher level. And that increase is delta Z, which is about 200 meters up the hill. The water is flowing in at a flow rate of 2 kilograms per second. And what we find that at the end, the temperature of the water has gone up by a little bit, hardly measurable, but it has gone up as a consequence of friction in the system. The water originally starts at 20 degrees, is heated up a little bit, and the tube has a diameter of 2 inches everywhere. Water comes in at atmospheric pressure and it leaves also at atmospheric pressure. Okay, assuming that this is a 100% efficient pump, what is its power required, or rephrased, what is the energy flow, the work that is done on the water from the pump? We can find that by a steady state. This runs in steady state by setting up a steady state total energy balance for the system. So we have 0 is, because it is steady state, energy balance. What flows in is the mass flow rate times the energy concentration here, that is internal energy, so temperature effects, Cp times the entrance temperature, kinetic, potential and pressure. And then what flows out here is again a Vm term, which is the same because it's steady state. Mass balance tells you what flows in must flow out, and outflow has an energy concentration, internal energy at a slightly higher temperature, kinetic energy, gravitational energy, you have lifted it up, and pressure energy. And I combine the in and the outflow in one step by writing them as in minus out of each of the concentrations. So this is the thermal effect. I need to add to that the difference in the kinetic energy. And I need to add to that the difference in gravitational energy. And finally, I need to add to that the pressure as energy concentration. And then I close these brackets. So this term is in minus out. Obviously, that's not the entire story. In principle, you could have added heat and you can add work. Okay, this is the full story. I can scratch out this one because it's a 0, as we don't add or subtract heat. These two are the same because the inlet pressure and the outlet pressure are both atmospheric. These two are the same because the diameter here and the diameter there are equal, and the mass flow rates are equal, as a mass balance will show you in steady state. Thus the velocities are the same and they go out. This is known, that is minus the delta T that we have. This is also known, that gives me a Z, a lifting, and it should be a minus in front of it because Z1 is lower than Z2. Okay, so I can now first take a look at suppose there was no heat effect, which comes from friction. Suppose there was no friction. How much work do I need to do to lift? Then you get out of this entire equation, also this is now ignored. All I have left, that work by the pump, so an energy inflow from the pump, the work that it has to do, is equal to the mass flow rate times the change in potential energy. Makes sense. All that you do is lift up the water, and the amount of kilograms per second is listed here, and they all get a gain in potential energy each kilogram of this value. If you do that and compute this, is 3.9 kilowatts. That's the power required just to lift up. But obviously there is friction, and thus you have additional input of energy as you are going via that friction to heat up the water. So in reality there is also this part. It is phi m times G delta Z what we had, but I need to add this part. Thus there is a Cp delta T term that is added. Now delta T may be very small, but Cp for water and for most substances are not small. This is 4200 joule per kilogram per Kelvin. And if you correct our first estimate for that, you see that there is some 10% of energy more required because you're losing here due to friction. You have to add that. Okay, 10%, is that much or is that little? Well, it's not too bad, but it's a loss term that is there. Moreover, your pump will probably have to be a little bit stronger. It needs to supply a little bit more power, as we assume that everything that a pump generates is turned into energy that is useful in this equation. In practice it's not. The pump will heat up itself, and there's a loss term. So the efficiency of the pump is less than 100%, and you need a heavier pump.